Everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. Today is the 11th 11th live discussion session that and so almost we are coming towards the end of this course, and after today the next Sunday we will be having the last discussion session, and after that on the next Sunday, this is on the 20th, we will having the 13th discussion session, and that discussion session is nothing but uh, uh, our uh, revision session. Okay, revision or summary session. Okay. Yeah, so let us continue with today's session, and what we are going to do is that we are going to begin today's session by just revising whatever we studied in the previous session. Okay, we'll just revise a bit very fast. We'll just skim through all the topics, and after that we will be actually starting today's session. All right. Okay, so let's see what we did the previous class. Okay, so let us see what we did in the previous class. I hope the audio is clear to you. Let me just check a bit. Okay, so let us see. Yeah, so in the previous class what we did was we basically discussed about filtration, right? So we dealt with the basic stuff regarding filtration. We saw all those things, right? So basically what we did was we saw what is filtration and how we can design filters. Okay, filters for a system. So filters can be soil filters, or we can have filters that are made up of geosynthetics, right? So there are various criterias, as you know. So we saw many criterias and how to implement those. Actually we saw all those stuff, right? So let me just directly go to the problem. Okay, so all these criteria we discussed, right? So in when so how to select a geotextile as a filter. Okay, this is the criteria. So for granular soil it's different, for clay soils it's different. So for both cases we discuss, so there are, so the main two criteria that we have to follow is, one is the permeability criteria, and second is the retention criteria. So we have to satisfy both of these, right? So we have to satisfy the permeability criteria as well as the retention criteria. Retention criteria means what? That we have to ensure that the soil is retained, and there is no loss of the fine particles of the soil. And the second is the permeability criteria, which ensures that there is optimum flow of water through the filter. Okay, right? So these are the main two criteria, and for very different types of soil these criteria differ. Then we saw this German guidelines. So German guidelines are described for two types of soil. One is the stable soil, other is the unstable soil. So when do we call this soil stable, stable, and when do we call a soil unstable? Those two are actually mentioned here. So gap graded soils are generally unstable soil, right? And the other properties of the problem soil or unstable soil, those are also given here. Okay, if you see whose D50 lies between 0.02 and zero point 0.1, soils with uniformity coefficient less than 15, and all of those stuff. So then we solve this problem. So for a particular soil, this D10 size was given, D50, D60, D90, all this was given, and we are asked to select a suitable filter method. Okay, so we use the German criteria to decide the size of the geotextile filter that we have to use. Okay, then we saw what the gradient ratio step test is and why do we actually do this gradient ratio test, and then we solve this problem. So these problems we are asked to check if which of the which of these constituent geotextiles are actually uh, can we actually use for this particular scenario. Okay, for this particular scenario that has been given here, which of the geotextiles from here can we actually use? So that we have to decide. So the first step was to calculate the permittivity, that is psi. So we use the flow equation to determine the permittivity, right? So then we get the permittivity. Okay, this is the value of the permittivity. Then we found the allowable permittivity of the geotextile. Okay, allowable permittivity of the geotextile. After that we check if the allowable by required is actually greater than a certain amount. Okay, if it is so, then it is acceptable. Okay, so we found out the factor of safety, and you can see that for all the three geotextile the factor of safety is good enough. Okay, just a second. just give me just give me 1 second. I will just reshare the screen. Yeah, so as I was saying, so we calculate this factor of safeties, and then we check. Okay, so we calculated and we saw that all of these results are acceptable. So this was the flow criteria, permeability criteria, right? Next, what we have to do next, we have to check for the retention criteria. So retention criteria, we use the Carroll's criteria, which says that the O95 should be less than 2.5 times the D85 size of the soil. And in this case, when we check the properties of the given geotextile, we see that only the geotextile 1 and the geotextile 3 can actually be used for the purpose. Okay. Now next is another filter problem that we saw. So here nothing, just here we have an under drain. Okay, we have an under drain here, right? So we have under drain here, under drain, then we have a geotextile that is lay it over that, so that we can just allow water to pass, and we can prevent the soil from this or this part to enter into the drain. Okay, enter into the drain. So similarly we solve this problem again. So first step is always to calculate the permittivity. Okay, so calculate that permittivity. This was the permittivity, and after that we calculate the allowable permittivity of the geotextile. So this is the allowable permittivity of the geotextile. Next we want to find out the factor of safety, and we saw that the factor of safety is very good enough. Okay, it's around 45, which is quite good. Okay, and then as usual the next step is to check the retention criteria. So this was the flow criteria or permeability criteria that we checked, and next what we have to do, we have to check for the retention criteria, right? So how do we actually check for the retention criteria? We use various criteria. So this is a chart that was given by Literature et al, where it is given in actually uh, Corner's book. So from there we see found for see if we see here, so you can see for various types of soil with different criteria is given, right? So for our soil we choose this criteria, that this criteria should be used for our soil, and then we check whether this is satisfying. So and then we find out that the current geotextile which is asked, which is given in the question, which is there in the question, cannot be used in the present scenario. Okay, so this was filtration, and next we have what next, a property similar to filtration, that is nothing but drainage. Okay, that is nothing but drainage. So in drainage what you have to do, you have to allow water to pass through that geotextile, right? Geotextile or whatever geosynthetic you used, right? So that is the purpose of drainage. So you have to carry the water through the geotextile and finally vent it out or let it out. So these are the various applications of drainage. We have maintained raised interceptor trenches on slopes, drainage behind abutments and retaining structures, relief of water pressure on body structures, substitute for conventional drains, leachate collection and gas venting, drainage mats in horizontal applications such as roofing, PVDs for accelerated consolidated of clay. So all these things, you will see the PVDs you already know, you have seen, and this leachate collection and all this also I discussed in the previous session, right? So I'm not going to repeat that again. So just let us see a problem or whatever that is given. So these, you can see, these are the various codes that are that we use for the drainage purposes. So these are made up of various materials, mostly polymers, and we can have various codes that actually are that is sandwiched between other geotextile, and that code actually carries the water. Okay, so then what we need the in-plane, you need to test for any geotextile. If you want to find out the its capacity for drainage, you need to do this in-plane drainage capacity test. Okay, such as the constant head test, where you allow the water to flow through the geotextile across a constant head, and then calculate the transmissivity. Okay, so here we calculate the transmissivity, and in case of the filters, what we did, in case of the filters we calculated what permittivity, and in case of drainage what we do, we calculate the transmissivity. Okay, these are the various recommended reduction factors for geotextiles. Okay, for geotextile, for used in various cases applications, and this is the same for geonets. Okay, reduction factors for the transmissivity of geonets. So now this problem we had solved. So what is this problem? So this problem here, we have a zoned earthen dam. Okay, earthen dam, 10 meter of water it is retaining, and you have a impermeable clay core that is there, and to drain out the water from along the clay core, what we do, we actually have a geotextile chimney drain that is placed there. So we need to calculate the factor of safety and check if the given geotextile is fine for this purpose. So again, the first task we will calculate the flow Okay, calculate the flow using the flow net, and from the flow what we need to do, we need to find out the transmissivity. So that is what we did here. So here you can see we first calculate the flow here, and from that flow what we did, from that flow we calculated the transmissivity that is required. Okay, after that what we need to do, we need to find the factor of safety again. Similarly, K level by theta level by theta required. Theta level is nothing but the ultimate transmissivity divided by the reduction factors, and then divided by the theta required, transmissivity required. So if we do that, you will see that the factor of safety comes 1.3, which is quite low. Okay, we generally need to greater than 5 factor of safety generally. So we require a factor of safety of 5 to 10. So since we got less factor of safety, we need to change the geotextile. Okay, and similarly, like the previous filtration thing, what we need to do is that we need to uh, so this was the what, it was the flow criteria, right? So next what you have to do, we need to check for the retention criteria also. Okay, so since we are just designing for the drainage here, so that's why I have not shown the retention part. Okay, but generally always there is a core, and that core geosynthetic core, and that geosynthetic core is sandwiched between two geotextile filters. Okay, so that's why you need to do the retention analysis, but here that is not our focus, so we do not do that. So then we have this problem. So here we have retaining wall and retaining wall, and so there is a drainage layer that is placed along the face of the retaining wall, and the purpose of the drainage wall is to really drain out the water so that we do not have excess of water pressure that is generated, which can be actually detrimental to the safety of the retaining wall, right? So this is what uh, okay, so this is what we have to do now. We have to check if the given geotextile, or what geotextile, non-vulnerable punch geotextile, is actually fine for this, for is suitable for this purpose, that we need to check. So similar to the previous problem, what we did first, we first calculated the flow, and after we calculated the flow, we calculated the transmissivity. Okay, this is the required transmissivity. Then similar to the previous one, we need to find the factor of safety allowable by required. We see that the factor of safety is very less, which is not even acceptable, nearly acceptable. So what we need to do, we need to go for some other geotextile. Okay, other geotextile having high transmissivity. Now this was one more question here what we have. So here we have a frozen food storage building. Okay, and so what happens, it is seen that there is some capillary rise of water from the bottom to the top. So what will happen if water rises above and comes near the building? Since this is a frozen food storage building, the temperature here, okay, in these regions it's very low. Okay, because since here the temperature is very low, outside also temperature is quite low. Due to that, what happens if this water freezes, this water is going to expand. You already know that if water freezes, it expands in volume, so it will expand near the structure, and this expansion of water near the structure might actually cause cracks in the building. So that we need to prevent. So for that purpose, what we did, we actually here what they have done is they have actually used a drainage system, so that when water comes up, it can be drained out. Okay, it can be drained out using this geotextile drain. Okay, and yeah, so right, you understand, right? So water is coming, water is rising up, it will be carried by this geotextile drain, and then it will be ultimately drained into this under drains. Okay, these under drains which are running along this length, it will be drained in that. So what is first to fast, this flow is given. The first step is always the flow. From the flow we calculate the transmissivity, and then we find out the factor of safety, and here also you are seeing that it is not acceptable. So now again similar problem. So here again we are using a geonet. In this case, instead of geotextile, we are using a geonet for the drainage purposes of the water, to drain out water from behind the retaining wall. We are using a geonet. Okay, So again, as usual, the first step is to determine the flow, then the allowable transmissivity, and then you have to what we have to do. So here we have a graph of the plot of the flow rate versus the normal stress. So if we increase the normal stress over a geonet, the flow is going to reduce, right? So for this particular geonet, this plot is given, okay, for various I gradients, for various, sorry, for various gradients. Okay, so for various gradients we have various flow rates corresponding to various normal stresses. So here first we calculate the average normal stress, and corresponding to this normal stress, we find out this ultimate transmissivity from the graph, from that plot, and then we divide this ultimate value by the reduction factor to get the allowable, and then we finally calculate the factor. So it is nothing but theta allowable by theta required. So it's around 1.4 and marginal acceptable. It is not actually acceptable. We need more factor of safety. Okay, so this was all that we discussed in the previous class. Okay, and I hope that it is actually clear to you. Okay, now let us go to today's. Okay, so today basically what we'll be doing, so there is nothing much to discuss today okay. So as you might have gone through whatever has is being, whatever was taught in the main theory lectures, main lectures, you must have already gone through those lectures, right? And you must have seen that this erosion part is not that extensive, right? It's quite simple, and I hope that you have already understood everything. So what we are going to do is just we are going to roughly summarize or roughly go through some of the things that were discussed briefly, very briefly, and then we'll be solving one or two problems. Okay, so slowly we'll be doing, as we have a lot of times, around 1.5 hours we already have. So slowly we will be doing, and slowly we don't have much amount of stuff to do today, so slowly we will be doing. So we will be studying whatever, revising whatever was taught in the class, and after that what we will do is that we will actually solve one or two problems, and then we will wrap up today's session. And in the and before we begin this part, let me tell you that in the next session, what we can do is that we can discuss about the geomembranes and all those stuff. Okay, so how do you actually use geomembranes? Okay, how geomembranes, so you know that I had discussed this briefly before, right? So why do you use geomembranes are used as liners. So you have slopes, right? We have the slope of the landfill, so where you have to put the geomembrane. So sometimes we need to strengthen those slopes, okay, so that slopes do not fail. So those part we'll see if we can will do, or what we can do is we will see how we put the geomembrane. So like how the stability of the geomembranes along the slopes of the landfill is maintained. Okay, how to decide the thickness of the uh, this soil that is there above the geomembrane, and how to discuss the embedment depth of the geomembranes. All those things we can actually discuss. Okay, we'll see that in the next class. So almost we are done with this course. Okay, almost you already have seen, almost this is the second last class, then you have one more class, and on the 13th session it will be just a hour 1 hour long duration session that we will just revise from the beginning to the end. Whatever we have studied in these 12 weeks, we will revise that everything the 13th week. Okay, so nothing much to do there. So just I will give you 2 minutes, just try to recall whatever was done in the previous session, and then we will continue with today's session. Okay, and also try to recall whatever was taught in this erosion topic. Okay, what are the concepts that are taught, and then in 1 minute, then I will start speaking in 1 minute. Okay. So I hope that whatever is being taught it's clear to you, right? So if you have any doubt, please feel free to ask me anytime, or stop. You can also stop me anytime and ask in between too. There is no issue. Okay. So if you have any doubt, please feel free to ask me. Okay. So what was there? So what is erosion, right? So first question is, what is erosion? So erosion is the process of detaching soil particles from the ground and transporting it away. Okay, so this, what is erosion? So you have a ground, so somehow there is a loss of soil from that ground surface, right? That is nothing but erosion. So so how does erosion actually happen? Erosion happens due to various forces such as wind forces. So if wind blows very fast, what will happen? It will carry the soil from one part and it will transport it to some other part, right? So that is called wind erosion. Then we have rain. So if it rains, also rain will wash away the soil from one place, right? That is one. Then we have currents. We have currents of river. Okay, if you have river flowing, okay, it will carry, it will erode away its banks, the banks of the river, which is a very, what to say, which is a very uh, big problem, okay, in many places, where due to this river erosion, the sides of the land is lost. Okay, huge amount of land is lost to the river, and due to this, what happens is that there is loss of a lot of loss of life and property also. So where people actually live very close to the river, what happens, their houses are destroyed and many such things happens, right? So the currents, then we have waves of waves in the sea and the ocean. They also wash away the coastline, right? Coast from the soil from the coast, it washes away, right? So these are the various forces. Okay, wind, rain, currents, waves, some of the few forces which are responsible for erosion. Soil on slopes is most subjected to erosion, right? So you have a slope, right? Say you have a slope, and you have a very open slope, slopey land, and so what happens if there is some slight disturbance due to, say, rain or something, what happens, as the soil is in unstable state, with slight application of some external forces such as rain, wind, or maybe seismic forces, what happens is that there is erosion. Okay, erosion of that soil. Okay, the soil actually comes down from the slope. So it takes more than 100 years to form 1 centimeter of soil. Just to form a 1 centimeter thick soil layer, it needs more than 100 years. So as you know, soil is from where? From various chemical and mechanical processes, right? Such as weathering and all those stuff, chemical weathering, physical weathering, and many other factors. So to form just 1 centimeter thick layer of soil, it needs about 100 years. So we need to prevent the soil erosion, the loss of soil. Now, what are the various problems due to soil erosion? As I said, loss of land, right? Loss of shoreline due to the high currents of the seas and the oceans. What happens? The shoreline gets reduced, right? A lot of land is actually lost because the high currents in the oceans, they actually break down the soil. Okay, the waves they come and they collide with the collide with the soil on the shore, and they break it down and they carry it along with it, right? So that is very difficult. So it creates a very difficult situation, right? Because the land amount of land area, it's getting reduced day by day. All right. uh, right. Then we have instability of the slopes. As I said, you have the slope. So if soil keeps on uh, eroding away from the slope, it makes that slope very unstable, right? So instability in the slope, loss of topsoil and fertility of soil. So the topsoil is very fertile, right? So all the microorganisms are there, everything. So the topsoil is really fertile, which is very necessary. It is very much needed for agricultural purposes. So what will happen if it keeps on getting eroded away in a way? So we cannot grow crops, right? So it is a very like very important thing that we should always we have to prevent. We have to prevent the erosion of the topsoil. Okay, else we won't be able to grow vegetables and crops. Okay. Then you have loss of reservoir capacity due to silting. So reservoir capacity due to silting means what? Say what happens when the river flows, it keep keeps on eroding away the river banks, soil from the river banks, right? And this soil in turn gets deposited into the river bed, and the capacity to carry that water of the river water carrying capacity of that river actually reduces, right? There is a lot of silting. That is a deposition of soil which is being carried by the river by eroding away the parts of the banks, river banks. So that causes silting, and due to this the capacity of the river or the reservoir reduces. And then what happens is that uh, say suddenly you have huge amount of rain for a week, and then the river, all the water, all the catchment area actually drains into the river, and then the river cannot hold a lot of amount of water, because due to silting the depth of the reservoir of the river is reduced. So in that cases we have floods, right? So this is also one of the big reasons. So regular dredging should be done. Okay, or we have to prevent the erosion along the bank. The rubber and tea plantation suffer most from loss of topsoil, because rubber and tea plantation, that is most important uh, for good growth of rubber and tea plantations, they need this topsoil. Okay. So this is a big problem. If the topsoil is lost, then you cannot grow good quality of rubber and tea. Yeah, so what are the different types of erosion forces? Okay, as I said, as we already discussed in the previous class, what are the different types of erosion forces? So wind, what is wind erosion? Due to high winds, high speed winds, the winds also carry the soil from one place to another. That is the wind erosion. Then we have erosion due to water currents, water, and then we have the gravity forces. Okay, these are the main. So what are the different types of erosion that we can have? So first is the aeolian erosion. Aeolian, from that aeolian word only you can make out that it is the erosion due to what? Due to winds. So wind blows away fine cohesionless soil. Okay, so if you have a sandy soil at some place, so if wind blows at very high speed, it's going to carry that cohesionless sandy soil from one place and transfer it to other place. So it happens. Okay. Then we have rain erosion. Rain splash and rain wash attack the land mass, so causing surface erosion. So if we have heavy rain, the flow of water from the rain, or the if we have high if rain is falling at a high speed, it can erodes the topsoil. Then we have river erosion, hydraulic lifting, scouring, cavitation, abrasion. All these things happen due to the action of the river. Okay. And river erosion also triggers mass movement in the form of landslip. So that is also a very it is also something that you have to keep in mind. Then we have marine erosion, wind caused waves and currents. Okay, so as I said, waves and the currents in the seas and oceans, this called, and the tides also, these all these things actually may lead to erosion. Glacier erosion. So glacier are huge deposits of ice that are getting deposited in the place thousands of years. Okay, very huge deposits of ice, and that ice actually flows very slowly because the glacier is heavy. It actually flows very slowly, and when the glacier flows, it also carries the soil with it. Okay, so glacial erosion is also a big factor. So here you can see an interesting table that is given on the left. So right, so wind speed, direction, cohesionless soil, large exposed area, lack of protected land to lack of protection lead to wind erosion. So you can see this table here where there are different size particle diameter, okay, size of the soil particles are given on the one side, and on the other side we have the wind susceptibility. Okay, so if we have lesser size particles, say less than 0.42, it's highly erodible. Then between 0.42 to 0.84 it's difficult erodible. Then 0.84 to 6.4 usually non-erodible, and if it's greater than 6.4 it is also non-erodible. Okay, so larger size mean to us it's heavy, right? So if it's heavy, it's difficult for the wind to carry it. Okay, it's difficult for the wind to carry it. uh, so we are calling it non-erodible. But if it is smaller size, lighter material, lighter particles, it can be easily carried by the wind. Then we have rainwater induced erosion. It's given here. You can see impact of raindrops means how fast or how is it impacting. So it raindrops falls from height, right? So it comes and impacts the soil. So this actually affects dislodges the, like it actually what does it do? So rain falls at a high speed from the clouds, right? So when it falls down into the surface at a great velocity, it displaces the particle which is there at that portion, right, at that location. Okay, and rapidly you can see rain droplets are falling, so it will actually disturb the whole area. Okay, it will loosen out the soil in that area. So you can see the different intensities of rainfall. It's given a drizzle, light, moderate, heavy, excessive, cloudburst. Okay, so uh, a drizzle, if you've seen very slight rain, it's happening less than 1 mm per hour intensity. Diameter is also very less. Then the kinetic energy per meter square per hour is also very less. But if you are having a heavy rain, so you can see the kinetic energy that rain is actually imparting in a location per meter square per hour, it's also getting higher. So this kinetic energy is getting transferred to the soil particles, and soil particles get disturbed and then get eroded out. Okay, so this is how this rainfall induced erosion happens. So and one more thing that I was going to say was that how, like, what are the factors that influence the rainwater erosion? Okay, depends on the energy distribution of the flash. Okay, that is the intensity. It depends on the intensity of the rainfall. Second is the erodibility of the soil, means how tightly or loosely the soil is placed at a particular location. Okay, the susceptibility of a given soil to erosion, so that is also important. So the clay content of the soil, the particle size of the soil, that all those things actually affect then the physical features of that region. The how is the topography, the gradient of the slope, right, presence of burns, vegetation, roads, all these things. Okay, this also actually affect. So what are the different protection systems that we have? So one is the riprap. So what are ripraps? What are ripraps? Can you tell me what are ripraps? What are ripraps? So let us see what are ripraps. Okay. These are ripraps. Ripraps are nothing but this graded large size of uh, what to say, graded large size boulders, or these angular large size boulders that are actually placed along the coast, or along the river banks to prevent the erosion of the virgin soil that is present there. So you can see a small river that is flowing. So this is a Wikipedia image. You can see here a small river that is flowing, right? See here in the, okay, this part. So you can see a small river that is flowing, and to prevent the erosion of the, obviously, so this photo is taken when the flow is less, but I am sure that when there will be rain, and the whole city water will be gushing through this part, or nothing to this small river or whatever is there. Okay, so to prevent the erosion of the river bank or these banks, what is done, they place these ripraps on the both the sides. Okay, so that it can take the force of the uh, uh, river, and it can actually prevent the prevent the loss of the original soil that is there. Okay, here also you can see a river is flowing in this picture. Here you can see the river is flowing, and you have a, what to say, uh, uh, riprap that is given here. Okay, so there's some many pictures you can see here. Okay, so these are nothing but riprap. So directly these boulders, or this angular graded big size boulders, are actually placed along the coast, close to the bank, not coast, the bank or the coast, whatever you want to say. Okay, this is riprap. So next, what do we have? Yeah, so riprap is on. Next is concrete lining. Okay, concrete lining is what? Concrete lining is nothing but you line the sides of the canal. So you say you have a canal. Okay, you have a canal, and you have a soil made up, just directly you have made that canal with this by dredging out the soil. So in that case, what is going to happen, when the water flows through the canal, it's going to erode the sides of the canal. So to prevent that, what you can do, you can line the, just you can line the sides of that canal with concrete, so that you can prevent the erosion. Then you have gunneting. Gunneting is nothing but shotcreting. That is spraying of concrete. Spraying of concrete. Let us see if we can get some image. Yes, they said shotcreting, right? Shotcreting. So you can see this is gunneting. The spraying of concrete. Okay, this spraying of concrete is nothing but gunneting. So you can spray concrete on the sides, uh, on the where in the slopes, wherever we want to prevent the loss of soil. Okay. Then we have Gabian mattress. So Gabian mattress you already know. Gabian mattress you already have discussed before also. Okay, what are Gabians you already discussed. So these are like this. Okay, these are, we have this steel wire mesh cages, steel wire cages that are made of steel wires, and then these cages are actually filled with these boulders. Okay, the cages are actually filled with these boulders to form the this wall like structure. Okay, wall like structure, these are called gabions. Okay, gabion walls. Okay, so we have steel cages, steel mesh cages, and these cages are actually filled with these aggregates, long big size boulder size aggregates. Okay, gabion done. Then geotextile covering you already know. Just we will place the geotextile on the sides to prevent. Then your cellular mattresses and net. Cellular mattress is nothing but your geocell. Okay, you place the geocell. Okay, geocell. You already saw these pictures in previous classes also, right? You already saw some of these things like Gabian shortcutting, geocell covering. All these things we already saw before. So I hope that you are able to. I hope that you are able to like like when we say these words, I hope that these things actually come to your mind. You're able to visualize actually how we are going to do those things. Okay, and I hope that you are able to do that. Okay, then we have bitumen asphalt spray, same like short treating. We spray bitumen. That also we can do. And yeah, and of course we can have vegetation, right? So vegetation means we plant some types of plant some trees, or plant some kind of vegetation that has got long roots. So those roots, if the root network of that plant is like that goes deep and wide, it can actually hold the soil in place, right? So that's why we say that deforestation should be avoided to maximum extent. So if deforestation stops, we will see that in hilly regions, mainly in India, we will see that if we prevent deforestation, we can also prevent the landslides and all those things. Generally, why such landslides and everything is happening in these hilly regions in India? Why is that, has it increased so much? This is because lot of the human activity, lot of construction is going on everywhere, and for that people are actually cutting down the trees, and they're removing the vegetation. All those things people are doing to construct houses and all these things, right? So that actually what that is actually that is actually making the slopes, hilly slopes, more susceptible to failure, right? Because previously what, so when we have trees, the roots of the trees actually hold the soil in position. Okay, they bind the soil together in position. Okay, but now if you cut down the trees, landslides are bound to happen, right? So that's why we need to give some thought in that and prevent deforestation in these hilly regions. We always, there is some alternative that we can adopt. Always there is some solution. Okay, that's why we are engineers, right? We have to give some different alternative solution. Cutting down trees and constructing something is the easiest method, but keeping the trees, preventing the erosion, and then continuing the development, that is what we have to do as engineers. That is the responsibility, that is our responsibility as engineers. Okay, so if you do not pay attention to this, what we are doing is we are cutting down trees at some place, and due to that a landslide will be occurring at some other place. Okay, so we are so say you have a hill slope like this. Okay, so you want to construct something at the top, so you are cutting down the trees at the top, and due to that what is happening, this you have, say you have a highway that is going down the slope at the bottom of the hill, and you cut down the trees at the top for construction, and for that what you are having, you are regularly now you are having landslides, a landslide that will ultimately go and block the highway. Okay, so that is not a solution, right? So some solution, there might should be some balance that we have to maintain. Okay. Okay, so yes, so these are all the pictures. So I forgot that I had put some pictures here also. So let us see. So these are some pictures. So this we already saw now, just now we saw. So this is what, this is riprap. This is the riprap that is placed, and then we have this concrete lining, that his lining is being done along the canal, okay, to prevent erosion when water flows through the canal. Then we have the short gunneting or short treating, and these are the cellular mattresses that are placed along the slope. Okay, then we can fill those geocells or cellular mattresses with soil, and then beautiful vegetation will grow easily in that slope, and that slope will get like we can prevent the erosion that way. Okay, then we have this geotextile. Okay, so you can see here and this image, so we have these white things are nothing but geotextiles. So geotextiles are placed to prevent the erosion. Okay, then here we have the gabions that are placed, the gabions. Okay, so this is what, so this is the how vegetations actually help to hold the subsoil. Okay, so here you can see we have the vegetation, right? And at the top we have the runoff, that is the water. If it rains or something, the water is going to flow like that. So it's actually protecting the subsoil below. Okay, it will hold, the roots will actually hold the subsoil together. Okay, that is the armor. So it is written as an armored layer provided by vegetation. So this vegetation actually acts as an armor. Okay, protection. Okay, it protects the soil from the this or erosion. So how does this so there are some uh, specific role that this vegetation does. So first is the interception. The first role is the interception. Interception is what? First, whenever rain it's falling, it absorbs the energy of the rain that is falling. It prevents the soil to get dislodged very easily because because it absorbs the energy of the rain. Next is the restrain. Restrains the soil with the help of the roots. The roots actually hold the soil. Okay, the retardation. Retardation is what? It increases the roughness of the soil. Let us say a little bit the soil started to dislodge. Little bit the soil starts to dislodge. But what will happen? As the surface is not smooth and it's made rough, that dislocation of that soil, some amount of soil will get arrested as the surface is not smooth, it's rough. Okay, and then this is the third, and then we have the fourthly we have the infiltration. Okay, so higher porosity and permeability increase the porosity permeability, then it will slow down the it will delay the onset of the runoff. Okay, so this deep so and then if you say we have very large trees that are there, trees have deep roots, right? So deep roots are going to actually hold the soil in position, that I said. These are going to reinforce the soil. Okay. So generally in India is very we have good amount of jute or coir and jute products that are available. Okay, so we can use jute and coir mattresses or jute geotextiles that we can place along the slopes of the hill, and that can actually as it is a natural thing, what we can do it can actually it is very sustainable, right? It's natural, it's not made up of any polymer, so it's very environment friendly. And then it also actually serve other purposes, similar other purposes that we discussed here. It will actually arrest the movement of the soil. Then as it is natural, the jutes are natural, easily plantations grow over that. So jute and coir mattresses or geotextiles, these are also widely used nowadays. So here I have put one small uh, what to say small question for you. You are to arrange the following soils based on their erosion tendency from most erodible to least erodible. So first you have to write the soil which is going to be the most erodible, and then last you have to write down the soil that is the least erodible. So please try to do this. Please try to do this. Let me see if you are able to do. So I'll give you 2 minutes. Please try to do this. So are you able to do it or not? It's very simple, right? There is nothing in that. It's very simple, just you think. So clay will obviously have less susceptibility, and then you also have to think about not just clay, we have to think about the size also. Gravels are large size, so can they get eroded very easily? So those things you have to consider. So what do you think, how is which is going to be the most erodable? So the most erodible is going to be our low plastic silt. Then we have this clay sand. Then we have uh, then we have MH. Then we have Cl. Then we have SW. Then least erodible is gravel, obviously, because it's highly heavy, right? Heavy. So polygated gravel is the least weight, and then the most erodible. Sorry, this polygated gravel is the least erodible since it's the is having the most weight, heavy, right? And then we have the silt that is having the highly erodible. Okay, highly erodible. So the complete chart looks something like this. Okay, this is how it looks like. Okay. Okay, so now let us look at this a bit. Sustainable infrastructure development and natural geotechnics. So what do you mean by sustainable infrastructure development? So sustainable infrastructure development means, say you are using a lot of polymeric geosynthetics, like say geomembranes or geotextiles or geogrids, whatever. Those are some polymers, right? And plastic type material. And you already know that this kind of material actually take a lot of time to get decomposed. Okay, hundreds of thousands of years to get decomposed. So these things are not at all sustainable, right? This is harmful to the environment in one sense. So we need to use natural geosynthetics as much as possible. That is one thing. And second thing is that if we use the naturally available geosynthetics such as coir and jute, if you want to use those stuff, those geotextiles made with coir and jute and all those things, what we can do, we can empower the local population which is there. So there are many villages and small towns where these are locally developed. So you do not need a very highly skilled labor to actually manufacture this kind of geotextiles made up of jute or coir. So you can employ the local unskilled labor, and they can actually get a means of sustenance, right? Using this. So you can give, so if you use more and more of this coir and geotextile, you will be actually giving work to this unskilled labor population, and due to that, what we ultimately, this our economy is going to get stronger, right? Because you are giving employment to these people. Okay, unskilled people, rural employment. So this gives increases a lot of rural employment also. So as I said, geosynthetics can help in aspect of sustainability, reduce the okay, so that is one case. Okay, that is one case where you are completely trying to shift to natural geosynthetics, or you are trying to promote the use of natural geosynthetics. It is one case. Secondly, even if we used your polymeric geosynthetic everywhere, say for reinforcement or whatever purpose, okay, so what you are doing, you are say if you are using, so just as an analogy I can tell you. So say if you remember, we had discussed about the design of thickness of unpaved road, right? So you saw that if you place the geosynthetic, our thickness of unpaved road was getting reduced. So what? So due to that, what you are doing? So you are uh, making less use of the aggregates, natural aggregates. Then you will be saving more on transportation cost also. So the carbon footprint ultimately you are actually reducing a lot. Okay, you are reducing a lot. So that is the main benefit of using geosynthetics. So geosynthetics are ultimately they are very much helpful for the sustainable infrastructure development, and also this natural, and it the impact actually grows by many fold if we use natural geosynthetics. Okay, as I said, natural geosynthetics, if we used normal geosynthetics, they help in one way. They are helping, they are sustainable, they are reducing the aggregate requirement and all those stuff. Okay, they are reducing the carbon footprint they are doing. But even over them, wherever possible, if you try to use this natural genetics, you will be contributing more to the sustainable development. Okay, how? Because obviously they are natural stuff, natural things. And also, secondly, we will be giving employment to the local unskilled rural people, right? Yeah. So generally, as I said, two main natural fibers are generally used for reinforcement. Natural fibers, so these two natural geosynthetics are made up of these, mainly these two. So one, we have jute, another is coir. One is jute, another one is coir. So these reinforcements made up of jute and coir can be used very nicely for reinforcement, erosion control, and all other purposes. Okay. uh, I recently had gone for a conference where one of the company had come. They actually deal with this your vacuum consolidation and the accelerated consolidation. They are specialized in that accelerated consolidation. So they also, so generally they said obviously this is the best. The normal PVDs that we use, the polymer made of a polymeric core. One core is there, inside outside we have the geotextile covering, right? So that obviously is the best. But they are also what they also showed me some of the samples where they have made constructed the this filter and the core with the help of this jute fiber. So they told me that they are trying to make it better and better. So obviously it is more sustainable, because it is natural. But one problem is that it will get degraded. The life is very short, right? As these are natural fibers, the life of these fibers is very less compared to the polymeric whatever PVDs you use. The PVD is constructed with the hello jute fibers. The life is quite less. So that is one challenge. And the flow rate that this is able to give, that is also one more challenge. So some design iterations have to be made. But yeah, I think in some years you can have a very good quality of jute PVDs and all those stuff. PVDs made up of jute and all those things. Okay, jute and coin. Oh, so what is jute fiber? You can see I put one image here, right? I have used one image here. So these are naturally growing fibers, and this coir is nothing but the your coconut. This coconut fiber that we have, that is the coir is made from that, derived from that. So I was speaking about that. These are PVDs. Okay, PVDs made out of this jute PVDs. But the main problem, as I said, is these are very short design life, because they get degraded very easily, and the flow rate is also quite less. But as years are going by, the development is rapidly going. So there I'm hopeful that in some years some technique will develop where you can have very good quality of PVDs, jute PVDs. Okay, then similarly choir also we can use for PVDs. Okay, then sequence choir mats are used like that. You can lay the whole choir mat on the slope so that it prevents erosion, and you can see after some years, so such a nice beautiful vegetation has grown over that choir mat. Okay. Then you have these cocoa logs, all those stuff, similar stuff made of jute and all those things that can be placed like this at the sides to prevent erosion. Then you can see NK stone column with the help of bamboo grids that are used, all those things. Okay. Okay. Now we will try to solve. So we have a lot of time, 45 minutes, but I think with how many problems? Let me check. How many problems we have? We have just two more problems to solve. So sorry, three problems. So you have three problems. So slowly we will solve. We have lots of time. I think it will be enough. So let us see the question. What the question is asking us to do. Evaluate the filtration adequacy of a candidate geotextile for placement beneath a rock riprap erosion control system. So riprap, I already told you. So we have these rock ripraps that are placed, and below that we have to place one for geotextile. The geotextile, the purpose of the geotextile is for filtration purpose. Okay, filtration purpose. So so what will happen? So you have this um, what is you have the slope or the this bank, river bank, or whatever. You have placed rock riprap. So this rock riprap, and below the riprap you place the geotextile. So geotextile, what? So water will come and it will come back. Okay, it will, as the water comes, say water level is high. Okay, when the water level reduces, what is going to do? It's going to, there is a tendency for the water to carry that soil along with it, right? So some amount of the impact will be reduced by this rock riprap, and the filter which is there, that is further going to prevent the loss of the soil particles from that place, right? It is going to allow the water to drain out, but it is going to prevent the soil particles to pass. So this is a coastal system. Okay? Coastal system, these ripraps are what, or these ripraps are going to absorb the absorb the energy that is coming from the energy that is coming from the uh, waves. Okay, waves and tides, that is going to dissipate the energy of the waves and tides. These rock ripraps are going to do that, and then to prevent the loss of the soil, we have placed a geotextile filter. The geotextile filter is easily going to let the water to drain out through it, but uh, it will prevent the passage of the soil particles. Okay. So evaluate the filtration adequacy of a candidate geotextile for placement beneath the rock riprap erosion control system in a coastal inlet area with 1 meter tide. So the height of the tides that generally have is of 1 meter. That is reversing flow conditions with moderate water current that's shown in the following. So water, when we have high tides, water is high; low tides, water height is going to reduce. The candidate geotextile laboratory properties are sensitivity of zero point 0.5 per second inverse and aperture opening size 0.21. The in situ soil is a beach sand, it's poorly graded sand with a coefficient of uniformity of 3.5, D 50.4, and porosity 0.4. Okay, so let us see to evaluate the filter adequacy, whether the this geotextile candidate geotextile is suitable for this purpose or not. Okay, whether the candidate geotextile is suitable for this purpose or not, we have to check this. So let us see. So what the first step is always to determine the flow condition, right? Flow and first condition is always to determine the flow, and from the flow we will determine the your permittivity or transmissivity, whatever we require. adequate flow, estimate the maximum flow rate due to 1 meter tidal lag. Assume the water profile as follows. So as I said, there is a 1 meter tidal lag. So high tide, it's 1 meter high, and low, but when it is coming down, it's coming down by 1 meter. And due to this tidal lag, when from up to down this water is coming down, there is a tendency that it will take the soil along with it. So that flow we need to determine. Okay, so we'll just draw. So we have something like this. So initially water level is something like this, then it comes like this. Okay, this is the initial, and this is the final water level. Okay, and the geotextile is somehow placed like this. No, geotextile is somewhat placed like this. This is 1 meter, and this we are taking approximately 50 meter. Okay, so Q max is 50 into 1 into 1 by 2 into 0.4 by 2, which is 5 meter cube per hour. Nothing but 1.39. Okay, so this is nothing but the porosity. So average porosity I've taken, and then average area. So like this we get the Q max. Yeah. So next we have second inverse. Okay, next you have to find the allowable one. So ultimate by reduction factors, soil clogging, binding, reduction factor, creep, reduction factor, intrusion. Okay, so these you can refer to the previous tables, whatever we had discussed. Okay, okay. So finally, therefore, we have to find the factor of safety. This is acceptable. Okay, okay, this is acceptable. So you understood, right? So you have water like this, water levels, and you have the geotextile place like this. So when water is coming from here to this level, there is a tendency for the water to take out the soil particles with it. That's why you put this geotextile here. Okay, it is the thing. Now 3 next part is what? Next part is the flow criteria is done. Next part is retention criteria. So retention criteria is if it is given is less than 0. Should be less than 0. 0.21 should be less than 0.24. So this is given. Okay, that's given. So this is satisfied. Okay, and it's okay. Okay, so this, so your flow and the retention both are satisfied. Now one more thing you should keep in mind is that uh, the geotextile shouldn't get damaged due to the wrap. So obviously first you are going to place the geotextile, and over that you are going to place the geotextile, and over the geotextile you are going to place the deep wrap, right? So you have to keep in mind that you should not damage the geotextile while you place it. Okay, while you place the deep wrap, you have to be very careful that you do not actually damage the geotextile. Okay, so this was quite simple, right? So one more simple problem, I will just show you the question, and I hope that this is clear to you. If you have any doubt, you can ask me. Clear, right? It is clear. It's very simple. Clear, right? We can proceed. We can proceed to the next one, right? Okay. So this is the next problem. So I will just give you 2 minutes. Just read the question and try. It's very simple. We solved previous problems also, right? It's a very similar problem. So I am hopeful that you should be able to solve this problem. Just try to solve this once. Try to read the question and try to think. The procedure is same as before. All the problems that we solved for drainage and filtration. Just try. Yeah, so did you understand the problem? You understood the problem or not? Same. Okay, yesterday we last class also we solved some problems. Today I also discussed the problems in the beginning, right? So this problem is quite similar to that. So it will determine the flow rate factor of safety of a geonet used as a primary leachate collection system above a geomembrane and beneath a sand covering layer in a landfill cell whose plan view. So plan view is shown here. The top view of a landfill is shown here. Okay, so the geonet delivers its flow to a certain perforated header pipe leading to a down gradient removal sum. So this is the top view of a landfill. So there are geogrid that is placed like whole area geogrid is placed. So the geogrid actually carries the leachate like this. It carries the leachate and it from here to in both sides. From the both sides it carries the leachate to this main pipe, and this pipe finally drains it out. Pipe really drains it out. The landfill is 35-meter high with a waste unit weight of 13 kilonewton per meter cube. So high you have 35-meter high landfill, and below at the base you have this drainage system that is there. So first you have sand, and below sand you have placed a geocell, and then geocell silently drain out, not geocell, sorry, geonet. Okay, so you have 35-meter high landfill. Below you have a layer of sand. Okay, uh, sand, and below that sand you have this geonet system that drains the leachate to a final drainage main header drainage pipe, and the header drainage pipe finally drains it out. The design inflow rate is given. Okay, so you need to find out the factor of safety for this flow that is happening across the geonet. Okay, that we have to find it out. So obviously as it is a geonet, so initially in the starting of the class we discussed that problem where you saw that the flow rate is actually a function of the gradient as well as the normal stress. So we need to consider the normal stress that the leachate, or not leachate, the landfill is imposing on the geonet. So for that purpose this height of the landfill is given to you, and also the unit weight of the waste that is given to you. Okay, so because so that you can determine the pressure, normal stress over a over the geonet. And from there, after you know the normal stress and you know the gradient that is nothing but 2%, and from using these two information, what you can do, you can easily find the flow rate, and that flow rate of the geonet, and that you can compare with the flow rate that you uh, get from the inflow of the leachate, and from there you have to determine the factor of safety. Okay, this is the question. So first we will see perpendicular to the central drainage pipe is LH. So this length, this is the maximum length, right? So this one, not the this one. This is the maximum length, right? 14 plus this thing. This will give the maximum length of the what to say length of the geonet that is there. So 14 plus this. This is what? So this is 5 degree. This is given, and this also you know this 150. So 150 times tan of 5 will get this, right? So we'll get 14 plus 150 times. Okay, so this will come 14 plus 30.1. Okay, next what is the flow rate that is given? Flow rate is given as 30,000 liter per hectare per day. So we need to convert it to proper units. 0.001 meter cube by hectares is 10 to the power 4 meter square. So this will come out as 0.003 meter cube per meter square per day. Okay, so this is the flow rate. So next we have maximum flow. So Q required flow rate is nothing but R times LH. 0.003 meter cube per day meter square times 27.1 meters. So it will be 0.003 times 27.1. Sorry, this is very blocky. Meter square per day per meter. That is 5.645 into 10 to the power minus 5 meter. So this meter cube. So meter cube per minute per meter. Okay, this is the flow rate. Meter cube per minute per meter. In just you have just converted the units. That's all. Now vertical pressure. Pressure is 35 is the height of the landfill times 13 is the unit weight. Is 455 kPa. And I is what? 0.02. So as I said, 455 and 0.02. 450 is something here. I is actually very less, right? If I'm not here, it will fall. Very less. So we take it as 0.003. So Q ultimate is this is the total reduction factor, okay? Cumulative reduction factor. Meter cube per meter. Therefore, final factor of safety is what? Q allowable by Q required. Is 2.885. What is the required? Required is this much. So obviously you can see that the factor of safety is quite high. So it is acceptable. It's acceptable. So we can use the we can use this particular geotextile for the required purpose, for this leachate collection purpose. Okay. So next we have the last problem for today. Okay, assuming that there are no regulations governing the situation. Governing the situation is the unit whose response is shown in the figure below. Educate for the following landfill lead detection and collection system. The unit lies between two HDP geomembranes and design flow is 10 times de minimis leakage. So this 100 times de minimis leakage. So this de minimis leakage is a fixed amount of quantity. Okay, de minimis leakage is a fixed amount of quantity that is actually defined traditionally. The minimum slope of the bottom of the 300 meter long landfill is 6%, and the landfill when compared with the 5 meter high with the unit width of is being 11. So landfill height is 5 meter, 50 meter, sorry, 50 meter. Landfill's height is 50 meter, and the unit weight is 11 kilonewton per meter cube. The waste. So from this again we can get the normal stress. 6% is the 6% is what? 6% is nothing but the gradient of the landfill. So that is also given, and the slope of the bottom length also given 300 meter. Okay, so first you will again find out the required flow, then the allowable flow, and then you will find out the vertical, then you will find out the factor of safety. Okay. Okay, so in this case what do we have a similar landfill. So in this landfill, say first layer like this geomembrane is there, then we have geonet that is placed not like this, maybe like this a geonet is placed, and again we have one uh, what to say, uh, geomembrane. So like this complete thickness of the landfill is actually formed. Okay, so and waste is actually here, and the height of this waste is how much? 50 meters. Okay, something like this. Okay, here we have to check same problem, similar, just values are different and something like that. Others everything is same. So q required 100 time d minimus, this value will take directly. It's actually given standard value from the book, I am directly taking it. 300 is the length of the bottom, so we'll get 2.08 into 10 per minute per meter. Okay, then we have vertical pressure, fifty kPa, I 6%, that is 0.06. So from here again 550 and 0.06, 505 till something here you will get something like that. So you can take 0.01 here between so 0.01 q ultimate is equal to 0 cube per minute per meter, right? Unit meter cube per minute per meter. Q ultimate by what? The cumulative reduction factor. Okay, this one. Try to do this one for me, please. Do this simple division. This one will come out as, this is total is 9.1. Okay, so factor of safety. What the hell, man? Okay, so this will come out as 53, which is more than adequate. Okay, so very simple, very simple. Okay, quite simple. Okay, so with this we will end today's problems. Okay, this was also nothing much as you saw. Very simple problems we solved. There were not too many things. And in the previous next problem, what we are going to do. So in the next problem, what next class, what maybe we will discuss these things. Okay, say we have a landfill, right? So uh, in a landfill you have this slope like this, right? You have slope like this, and mm, in that case, what you have to do generally, you place the geomembrane say like this here, right? This like this you place, and then you anchor it something like this. Then you have a layer of soil that is covering here, so thickness of h. So all this case, in these cases, how, what is the factor of safety of this loss, this slope, all these things we will try to develop. Okay, these things. Okay, and we will see how this anchor, how to anchor, what are the forces that are mobilized here, and all those things in brief. What we'll be doing is that we will discuss in the next class. Okay. Okay, and I hope that till today, how much whatever was discussed to you, everything was clear, right? I hope that whatever is discussed is clear. And if you have any doubt, please feel free to contact me. I am available always. So, and yeah, all these videos are also recorded and uploaded in the YouTube channel, right? So you can always refer to those whenever we want. You have some confusion, you can see this, refer to them anytime. And also all these problems whatever we discussed, these are also uploaded. All these PDF files are also uploaded, so you can refer to this. And what I suggest is just please try to solve all the problems again and again very nicely, and in the fashion that Professor Rajagopal has solved in the class. So please solve in that way, and practice all the problems that are discussed in the main class. And these problems also we can solve again and again, so that you get a good grasp over the things. And in the exam you need to solve all of this stuff very fast, right? So if you practice more, it will be more beneficial to you. Okay, and I'm hopeful that after because you put a lot of effort in this, and I'm hopeful that all of you will be actually performing good in your NPTEL certificate examination for this course. And so before we end, let me just write about the next class. So next class, not class. Every time I write it is class. This is not a class. Okay, this is just an informal interactive session. So next live interactive session will be on when, let me see, next Sunday. What is the date? 13th. Sunday, 13th of October 2024, 3 p.m. to 5 p.m. Okay, so this will be the penultimate discussion session, 2 hour discussion session. And after that, on the 20th, after this session, on the 20th 20, we will be having one more session, uh, that we will where we will actually discuss uh, uh, everything from first to the end. We will just revise very fast within 1 hour. We will just skim through all the topics, and we will just revise. And if you have any doubts, of course you can ask me. Okay, we'll just revise all the topics from the beginning to the end. Okay, so with this we will end today's session, and I am here. We all have 5 minutes remaining, right? So I am here till 5 o'clock, and if you have any doubts, of course you can ask me, or if you don't have any doubts, you may leave the session. Okay, but I will be here till 5, and even later if you want, you can always write to me anytime, and I will try my best to solve your doubts. Okay, so thank you so much for attending today's session, and I hope to see you again in the next session. Okay, thank you, and have a very good evening.